Okay, we're finishing off the properties of an autonomous differential equation. The first property was about solutions to a differential equation, the autonomous differential equation. Second property was about stability. We have two different kinds of crossings there. And then the third thing I wanted to talk about that we didn't get to was concavity. Okay, so we know that if the second derivative of y with respect to t is greater than 0 at a point A. In fact, let me just go ahead and put a point A in here, greater than 0. Then we say that y is concave up at A. Okay, so similarly, if the second derivative at A is negative, y is concave down. So it looks like a kind of happy, the curve. Some people will say that the curve is happy here, or some people would say the curve is holds water here, and here the curve is sad, or doesn't, or sheds water. Okay, so now if we have the dy over dt is f of y, this is the tricky bit. What is the second derivative of y with respect to t? Okay, so it's tricky because on the left hand side of the equation is the derivative with respect to t, so the second derivative would just be another derivative with respect to t, right? So that's just the normal second derivative. What's tricky is on the right. And why is this tricky? Because this doesn't depend on t, except through y, right? And so we actually have to use the chain rule here. This is going to be df dy, because f depends on y, times dy over dt. And you'll notice that if you were to cancel these, right, then you would have df over dt, which is what we wanted. Okay, so what we've just shown then is that let me change color back. The green is hard to see. What we've just shown then is that the second derivative of y with respect to t is equal to df over dy times dy over dt, but dy over dt, going back to the original equation, is f of y. So therefore we could write the second derivative this way. And now the second derivative with respect to t is written in terms of y. So let's see what that means in terms of the y prime plane. Right, so let's do a simpler example. Here's our function f of y, right? And we have our two equilibrium solutions. We have that y is decreasing here, y is increasing here, all the way from here to here. Okay, and then y is decreasing afterwards. And so now we want to think about the concavity, right? And so at these points where the curve is increasing, we would say that df over dy is greater than 0, right? So df over dy is greater than 0 from here over. And then for these points, df over dy is less than 0. Okay. Finally, f of y is either where the curve is above the axis or below the axis. So I'm starting to get too much stuff here. Let me erase some of this stuff so we can see it a little bit more clearly. Well, okay, let me just start over again. We'll get this out of the way. Okay, come on. Let me put a pause on there. Okay, so we're back with the redrawn graph here. And I'm going to be cutting up the positions where either f changes sign or df over dy changes sign. So in this region, right, we have that f of y is negative and df over dy is positive. So therefore in this region we have concave down. this region, f of y is positive, df over dy is positive, so therefore the curve is concave up. Then in this region, f of y again is positive, but df over dy changed sign on us, and so the curve is concave down. And then on the outside interval here, our f of y is negative, df over dy is negative, and so negative times negative, positive, concave up. Okay, so let me go ahead and put in some numbers here. -1, maybe 1, 2, and so let's draw our picture of our graph here. So we have an equilibrium at -1 and an equilibrium at 2. And then less than -1, we see now that we're decreasing and concave down. So decreasing and concave down means that you're looking like what? Decreasing, concave down looks like look like that. Right, so here we have curves coming down. Right? And so now here we change concavity. What is this point? It's a little less than 1, so maybe this, let me draw it in a different color here. Let's say that this y value is this y value right here. And so what we see here is that we're changing concavity from concave up to concave down, but the function is always increasing. Okay, so in this region then, it's always increasing, but we have a change in concavity, concave up to concave down, concave up, concave down, concave up, concave down, up, down. Okay, so you see what's happening there. Okay, and then finally above that we have our curve is decreasing and concave up. So it looks like we have a function coming down just like that. Very good. And so now this is actually this is ty, right? This is actually a pretty accurate picture of the solutions to this differential equation. Okay, we even have up to second order. All right. So just as a review, then we can now figure out where. Let's see. Let's say increasing, decreasing, concave up, concave down. Okay, so increasing and concave up would look like what? I think it would look something like that, right? Increasing concave down would look something like that. Decreasing concave up would look something like that. Decreasing concave down looks something like that. Okay, and so it's nice to have these kind of pictures in mind as you're drawing the graphs. Good. Okay. Now let's just try a few. We've got a couple minutes. We're going to just try a few random problems. Good. Question. Suppose that y prime is equal to cosine of y. True or false? It's possible that solutions are periodic. Go ahead and hit pause for a second and think about it. Okay, are you back? The answer is false. This was kind of a trick question because I put that cosine in there because that's periodic in y, but when we say that solutions are periodic, this periodic means periodic in t. And so did we say that solutions to an autonomous differential equation could be periodic? No, they cannot, because once the solution comes up, can it ever come back down? Can you ever do that? No, impossible. Good. All right. Question. Whoops, let me change colors again. It is possible to have two stable equilibrium solutions and no unstable equilibrium. Hint, I'm going to assume that f of y is continuous. Continuous. Go ahead and pause if you want to think about it. Okay, let's see what the answer is. It's easiest to visualize this on the y prime plane, because if we have two stable equilibria here and here, then what does the curve look like? What kind of crossings do you have? Well, you have those negative crossings, right? And so the question is am I able to get from this part of the graph to this part of the graph without crossing this line? Do you recognize this setup? This is the intermediate value theorem. The intermediate value theorem says that if the function is continuous and you have your function on both sides of the axis, then at some point in between the function must cross. And by the way, at that crossing, what kind of a crossing do you have? Unstable. Okay, so it is not possible, no, if f of y is continuous, which is typically what we have. So good, I think that's it for now. Try to take a look at some of the homework problems. This is kind of a fun section because we're not really doing any algebra. Everything we're doing is geometric. All right, see you in the next section.